Okay, so as I just mentioned to you, and I want to just reiterate one more time, right? We do a series of raw data traces where we look at formation of product, let's say as some absorbance over time, and we're going to do a whole series of these at different substrate concentrations. So our lines are at different substrate concentrations. So we do a whole bunch of different assays in the lab. And then we're going to measure our rates on the linear portion of the curve, and we're going to plot versus substrate concentration the observed velocities. And it's over here where we observe saturation, right, of the system. And that's going to determine where is Vmax. That's our limit line, and we get our Km from this plot of our process data. And that's our process data. Now, one other thing that I want to mention to you is that when we run these different assays and we look at our raw data traces in the lab, where we run the different assays at different substrate concentrations, and we see these lines fall over, this is not saturation. You're not looking at saturation on these plots. We don't see saturation here. What are we seeing? We're seeing essentially departure from the steady state. That is not the same as saturation, right? So we see saturation on these plots of V naught versus substrate concentration. We see departure from the steady state on plots of product accumulation, substrate disappearance, right? Measured as absorbance or whatever. Experimental way we have of monitoring that. Per unit time, we see departure from the steady state. So I just wanted to go over that. All right, so we get graphs that look like the graph that you see here, right? And from the graph that you see here, we're able to measure, right, what is our Km, right, and Vmax. If we wanted to, we could transform this data and do a Lineweaver-Burk plot where we are measuring a straight line relationship between the reciprocal of our initial velocity. And so our y-intercept is 1 over Vmax, and our x-intercept is minus 1 over Km. So we take and we make these plots of our experimental data, and then we can measure the values that you see here. So here's Km. Now you're looking at different substrates for sarcosine oxidase, and you're looking at this is sarcosine, this is dimethylglycine, or excuse me, this is N-ethyl glycine, and this is proline, right? Now, if you're wondering about down here, pipicolate or pipicolic acid is similar in structure to proline, and dimethylglycine is similar in structure to sarcosine, except that we have an extra methyl group. So sarcosine is also known as N-methylglycine, right? So that's also N-methylglycine. Now, if you were to rank these substrates in order from best to worst, based on the Km, which one would you pick as the best? Right? Sarcosine. I'm sure you'd pick sarcosine. Why you would choose this? Because it has the lowest Km. And oh my goodness, what is Km? Km is the substrate concentration at which the enzyme runs at half maximal velocity, right? Km doesn't tell you how tightly the enzyme binds the substrate. But you know, what's buried in there, Km is equal to K minus 1 plus K2 over K1. And if you think about our simplified right, we have K1, K minus 1, K2, right? What is KD? KD is the first order rate constant for the decay of the ES complex. So in this case, KD, K minus 1, right? So KD is in there. Alrighty. At any rate, let's go on. Now, let's consider another factor. So Kcat max. This is essentially, right, the maximum turnover number. This is K2. And just one thing that I want to point out is that these constants are apparent because we have only varied one substrate. So remember that, right, oxygen is a substrate for sarcosine oxidase, and in these assays, the concentration of oxygen was not varied. More about that in a minute. Now, let's look at these compounds again. Still, we have sarcosine, which is N-methylglycine, and we have N-ethylglycine, and we have proline. Now which one do you think is the best? Well, now you got something to consider, don't you? Because if we look at the previous slide, without question, sarcosine was really, really great, and boy, oh boy, wasn't N-ethylglycine terrible? Look at this Km. It's horrible. But now if we look at this 260 millimolar Km in the context of turnover number, so how is the enzyme at spinning out product per minute? Doesn't seem so bad anymore, does it? Now N-ethylglycine doesn't look too bad. Well, yeah, proline we've solidified as pretty much a worst case scenario here, because this turnover number is terrible, right? So if we rank the goodness, right, of these substrates based upon these different values, certainly sarcosine is the best according to Km, and it's the best according to the turnover number. If we were to consider just the Km, we'd say that N-ethylglycine is terrible, but in the light of the turnover number, doesn't look too bad, does it? Right? So, maybe this is okay. Maybe N-ethylglycine is okay as a substrate for this enzyme. So let's look at another way to evaluate the substrate preference of sarcosine oxidase. Let's look at this. This value is the gold standard. And it allows us to compare how good of a catalyst an enzyme is across multiple enzymes and multiple substrates, right? So this is the catalytic efficiency, and this is expressed as Kcat over Km. Now, if we look at the catalytic efficiency of the enzyme, we consider what is the we consider what is the amount of substrate to reach half maximal velocity for that enzyme reaction, and how quickly can the enzyme convert substrate to product. So that's the two factors that are considered in this a measure of catalytic efficiency, Kcat over Km. So this is essentially the turnover number divided by your Km. And clearly, now we've got a clear winner. Sarcosine is the winner here. It's got the greatest catalytic efficiency. We've pretty much confirmed proline is in last place. It's a terrible substrate for the enzyme. And then we have here our N-ethylglycine, which, wow, we went from looking only at the Km, we'd say that this is bad. And they say, oh, this is, well, maybe N-ethylglycine is an okay substrate. And then when we look at the catalytic efficiency, we get a clear picture. We say, it's not awesome. All right, so let's look at some other enzymes and as a measure of what is catalytic efficiency. So this is a table from your textbook. And if we look at which enzyme is the best, if we look at just the Kcat, which is essentially V2, right, on our simplified reaction equation, it looks like catalase is the best one here because it has the greatest catalytic rate, so the greatest rate of formation of product. If we look at what is the Km, we're going to be looking for the lowest Km. And now it looks like fumarase, when it's using fumarate as the substrate, is the best because it has the lowest Km. But when we consider the gold standard measure of catalytic efficiency, now we see that neither catalase nor fumarase, using fumarate as a substrate, is the winner. The clear winner here is an enzyme called crotonase. And crotonase has a Kcat over Km, which is pretty darn near the diffusion controlled limit. So this is as good as it can get. If you look at our simplified reaction diagram, do you remember this? I think this was a question on a Nearpod. What's the rate limiting step? Why is it the rate limiting step? This is your rate limiting step. Why is it rate limiting step? Because it is moderated by diffusion. And diffusion is going to be required for the bumping together of enzyme and substrate in the proper orientation in order for binding of the substrate at the active site. So this rate limiting step is governed by diffusion, which is, right, this is a slow and random process here. And so that's why we can never have catalytic efficiency which exceeds the diffusion controlled limit. When we talk about diffusion controlled limit, we're talking about how diffusion, right, the rate of diffusion is going to limit the combination of substrate with enzyme. And the last thing to look at are these steady state assays. Now, sarcosine oxidase, we're looking at sarcosine, oxygen, and water, which can be combined to give us formaldehyde, glycine, and hydrogen peroxide. So if, we're not going to consider water because we can't vary it. We have to vary two substrates. If you want to have the clearest picture of the parameters for an enzyme, how fast it works, and what is its relative affinities for substrate, you need to vary both substrates, and you need to do a lot of assays. So varying sarcosine, not a bad thing. It's an alternative. It's a non-proteinaceous amino acid. It just doesn't get built into proteins. That's easy, right? That's a compound. You buy it, you weigh it out, and then we got oxygen. And you need to be able to vary oxygen in your system. Oxygen is a gas, and at any rate, you can purchase specialty gases which are made to a particular specification that you tell the supplier, say, oh, I want to have 10% oxygen with balanced nitrogen. They'll make it for you. They'll certify that that's exactly what's in there. And then you need a system to deliver the oxygen to your system. So I was pretty proud of this setup when I was a grad student. I made this. And anyway, the concentration of oxygen in a liquid is very temperature dependent. So as is the rate of your enzymatic reaction. So you have to keep everything at a seriously constant temperature here. And anyway, you can't see down the bottom, but these are the screw caps. These are black screw caps on the reaction cuvettes, which are here in the picture, and they're quartz cuvettes. So anyway, there's a bubbler here that is equilibrating the oxygen gas, and anyway, by using excuse me, different concentrations of oxygen gases, I was able to vary both substrates, oxygen and sarcosine in the system, and use an alternative substrate here called N-methyl-L-alanine, and be able to measure true Km values. So see where it says these are not apparent Kms, these are true Kms, because they were determined by varying both substrates. And at any rate, by doing this, I was able to also clarify what is the mechanism for the enzyme. As far as, does it go by a ping pong mechanism? Does it go by a ternary mechanism? And the values that you see in parentheses were the values obtained with the N-methyl-L-alanine. At any rate, you can see that if we do individual regressions versus these other types of fits, the individual regressions line up well with the global ternary mechanism. So by doing these types of kinetic studies, you can also discern the mechanism for an enzyme. So you can get kinetic data used to support the enzyme mechanism as well. So kinetic data is not just used as a measure of how efficient or how good an enzyme works, but it can also tell you some information on how that enzyme is working.